Ôi bánh điện tử. Bánh cái gì? Buồn quá. Làm quả chuỗi cao thủ anh em. Đánh nôn nó cao với mày đấy. Cũng gặp ba đánh báo. Anh dê nó hơi kỳ. Thằng bạn tao bảo thằng dành con lắc mày kỹ quay ra lỗ thành có mấy ông giáo sư, một đống giáo sư đã xông vào đấy gạ kèo đi gặt giò, gạ kèo gặt giò không biết được
So let's begin the class. So on the screen you see what we studied last week. Last week we begin our lecture on determinants, the determinant of a square matrix. And we begin with a very elementary definition. If the matrix is outside 2 by 2, then determinant will be the number like that on the right side. And then we will define determinant of any square matrix of any size by inductively, by inductions. First, we know that we define already for any 2 by 2 matrix, and then suppose that we define already for any n minus 1 by n minus 1 matrix. Then, if we consider n by n matrix A like that, in order to define determinant of A, first of all we choose any entry, say A and J, and then we delete on the i's entry. It means that we delete entirely the i's row. It means that we delete the whole row containing A and J. We do the same thing for the columns, means we delete the whole J's columns. That is the column containing the A and J. And after deleting the i's rows and J's column, they left smaller matrix. That is a matrix outside n minus 1 by n minus 1. And that smaller matrix we know already determinant. And that determinant will be denoted by Mij. And we call it the minor of entry A and J. Or in Vietnamese we call it định thức con thứ EG. There is one more notion, that is the cofactor of Aij. The cofactors of Aij is different from the minor Aij only by the minus 1 to the power I plus J. That. And with the definition of a cofactor, we can define determinant of A. Then determinant of A can be given by one of those formula, A or B. The formula A has named cofactor expansion along the i's row. The I can be any row, the first row, the second row, up to the nth row. And the formula B, that is the cofactor expansion along the J's columns. And that column can be the first column, second column, or the last column. You can expand it along any rows or any column. It gives you the same result. And that result will be called the determinant of A. And after that, we have a practical rule to find determinant of any matrix of order 3. It is illustrated here. You add 2 more columns on the right side of A, and then we add the 3 product by going down arrows, and then you subtract the 3 product along the upper arrow here. Then determinant of A will be that. Tôi luôn luôn có một điều phàn nàn là các bạn ở cái góc phía kia kìa, nói to hơn thầy giáo. Cái phàn nàn của tôi là các bạn có thể đi về ạ, không cần ngồi đây ạ. Còn nếu các bạn ngồi đây thì các bạn giữ trật tự. So let's go. We continue. Up to previous slide, we know how we can compute a division of a square matrix, and it costs you a lot of calculation. And here in the next few slides, we know another way to find determinant. The first one, we define three notions of a special matrix. That is a triangular matrix or diagonal matrix. The first one is upper triangular matrix. That is all entry below the main diagonal must be 0. And the lower triangular matrix, that is all the entry above the main diagonal must be 0. And the diagonal matrix, that is a matrix which is both upper triangular and lower triangular. And in the class previous week, we have the illustration for that. We have an example of that. And here you can see we have an upper, lower, and diagonal. And for those triangular matrices, we have special formula to find determinant. The determinant of triangular matrix is very easy to calculate. It is a product of all entry lying on the main diagonal. Then the next we want to use elementary row operation to compute the determinant of a square matrix. And here I repeat for you what is the elementary row operation. And when we apply those operations, we get the following property. When we apply the row operation, the determinant of the result will be exchanged by that one. And of that, we summarize it in the property, I call it the property number P. Then we can use those operations to find determinant by 3 steps. I summarize it here. The first one, we try to use those operations to transform any square matrix A into row echelon form. But we know that for a square matrix, when it is in row echelon form, it is already in the upper triangular matrix. And for that, it is very easy to find determinant. Then, finally, the final step, we need to use the property P to find the determinant of A. And then, because we have by definition of determinant, we have the formula A and formula B. And that want to say that the determinant of A equals the determinant of A transpose. It means that anything in computing determinant of A, anything we do for rows, we can do the similar things for columns. And because that, here I define the elementary columns operation that is quite similar to that for rows, just only replace rows by column. That is Cij means we exchange the i's column and the j's column, and Cik means we multiply all the entry lying on the i's column by the number k. And the last one, Cij to the power k, means we add k times of i's column to the j's column of A. And then again we can apply those operations to change any square matrix into the upper triangular matrix. And when we apply those operations, that determinant will be changed like that one. And once again, we put it in the red frame. We can use that to calculate the determinant. And that give you some criteria when square matrix will have zero determinant. And we are going to use that today. We have three conditions, three criteria to see when square matrix will have zero determinant. And then after that, last week I give you a table compare two methods to calculate determinant. And obviously, if we follow the cofactor expansion, it costs you a lot of calculation, a lot of addition and multiplication. While if you follow the elementary row operation, the number of operations you need to use in computing the determinant is much less. But however, usually you can apply what we call the combine method. That is one step you can apply operation, rows operation or columns operation, and then the next step you can apply the expansion. It's up to you to choose which one you like. And here is an example. If you are required to find determinant of the A like that, A is big enough for you. But however, if first we apply the row operation like that one, then you get a new matrix with the second columns containing only one non-zero entry. Then obviously here you can expand along the second columns. And again, if we continue it that way, you will get the last row containing only one non-zero entry, that is the number 1 like that, and so on. You can continue it this way. So we see in these examples, one step, the first step you apply rows operation. The second step you use cofactor expansion. The next step you apply the columns operation, and then once again you apply the expansion, and so on, and finally you get that one. So it's up to you. You need to look at your concrete exercise to choose which methods you can apply to calculate the determinant. So that is almost on what you studied last week, and we continue from this point. So we continue to study some property of determinant. The first property we studied already last week. It says that the property of the product of AB equals the product of two determinants. The formula is on the screen like that, you see. And that we verify with elementary row operation already is here. But however, the second property want to tell you the determinant of the sum A plus B is in general different from the determinant of A plus determinant of B. you can find some counterexample for that. But however, here that property is true for any square matrix of A and B and of any order. So I write it only in the side in the order 3 by 3. It's easier for you to follow. So the property saying that if on entry of one rows of matrix A is the sum of two summand, then the determinant will be the sum of two determinant. Or in Vietnamese or in the Vietnamese textbook, it says that nếu mọi số hạng của một hàng trong ma trận bằng tổng của hai số thì định thức bằng tổng của hai định thức. So it is here. Sorry. You see, here you have that entry is a sum of Z1 and Z1. That entry is a sum of two summand here and the same. So in the first determinant here, we take the first summand here, we take A21, A21, A22, and A23. And for the second, we take the second summand here, B12, B21, B22, and B23. That is a property for determinant. And because anything we have for rows can be the same, can be true for the column. So we have similar thing here. You see the second column here. Each entry is a sum of two summand A12, B12, A22, B22, and A32, B32. So the determinant will be the sum of two determinants like that. And here examples for you to verify that example to give you. You can verify the first property, that is the determinant of product two matrices equals the product of two determinants. So given A and B is like that, let's continue then. You can verify that determinant of A equal minus 7 and determinant of B equal 11. Now the next one, first we forget the property. First we multiply A and B. What is that? Multiply A and B, we get a new matrix of size 3 by 3. And that matrix will have a determinant minus 77. And we can verify that it is exactly that one. Because the determinant of A is minus 7 and determinant of B is 11. So that is satisfied. The next one, we have to verify. Suppose that C is a number and we multiply the number C with the matrix A. CA means we multiply any entry of A by the number C. Then determinant of CA will be C to the power n multiplied by the determinant of A. And here is an example. A. We have A to be like that. You are required to find determinant of A. But it is very easy to see that A is 10 times of the matrix on the right hand side, and the right hand side, the matrix on the right hand side has a determinant equals 5. So by the property over there, the determinant of A, here you see A equals 10 times of that matrix. Then because that determinant of A will be 10 to the power 3 multiplied to determinant of that. But that equals 5 and 10 to the power 3 equals 1000. So our reason is 5000. Yeah. And that one will explain to you. A matrix A is invertible if and only if its determinant is non-zero. And that one is very important because you remember that sometimes you are required to find the inverse of matrix, and that one will be one of the criteria to see when a matrix is invertible or not. And that will be explained as follows. Why that? That is because first we consider I to denote I is identity matrix. That is a matrix has its own entry 1 lying on the main diagonal A. On other entry as 0. Then the determinant of identity equal 1. And suppose that A is invertible. We remember that A is invertible if and only if we can find a matrix denoted by A to the power minus 1. So that A multiplied by A to the power minus 1 equal identity. Now here we have on both sides we have matrix. Two matrices equal each other, so determinant are the same. Determinant on the right hand side is 1, and determinant on the left hand side. The left hand side here, determinant of A multiplied by A inverse equal determinant of A multiplied by determinant of A inverse, and you see that is a product of two number. Product of two number equal 1. So each of the number must be non-zero. Tích của hai số bằng 1 thì cả hai số đều chắc chắn phải khác không. That is determinant of A must be non-zero. So that explains to you why you have that. And here examples. Suppose that you are given A and B, and you need to verify which one is invertible and which one is not. So it is very easy for you because now you can calculate determinant. Determinant of A equals 0, so you can say A is not invertible. And the next one, determinant of B equals minus 12, it is a non-zero, so we say B is invertible because it has an inverse. And also from the previous slide, we see that in case A is invertible, then determinant of A inverse equals 1 over determinant of A. So I don't have to explain that to you. And that one again here just only to recall some property. I say it already from the very beginning. That is a determinant of A and determinant of A transpose are the same. And here, suppose that you are given A like that, you are required to find determinant of A inverse and determinant of A transform. And obviously, the first step, you need to know if A is irreducible, or otherwise you don't have an A inverse. And here, you calculate that determinant of A equals 4. 4 is non-zero. So you know that A is irreducible, and then you can write A to the power minus 1 or A inverse. And determinant of A inverse equals 1 over determinant of A. And because of that, determinant of A inverse equals 1 over 4. And here, determinant of A transpose equal determinant of A equals 4. Like that. That is the example here. And once again, I recall you that things. A is a square matrix. Then we have the following equivalent. The first one, we say that A is irreducible. And then Ax equal B has unique solution for any right hand side B. That is grammar rules. And by the end of today, you will see the grammar rules once again with very concrete formula. And then the number 3 saying the homogeneous system Ax equals 0 has only trivial solution because it has only one solution. And the last one is the determinant of A must be non-zero. And we have just said that A is irreducible if and only if determinant of A is non-zero. So we have 4 criteria here are equivalent to each other. From one property you can imply any other property. And here are examples how you can apply those conditions. You are given 2 systems of linear equation like that, and you are required to determine which of the following system will has unique solution, means it has only one solution. So we write it in the matrix form. It is Ax equal B. For the first equation, you will have determinant of A equals 0. And because that, the system does not have unique solution. For the second one, for the second system of linear equation, we write it Bx equal B. And B has, now you see, B has a determinant minus 20. It is a non-zero. So the system will have a unique solution. And by the end of today class, you will see how we can find the solution of that. Now the first, that notion is the new one. And I can tell you that you have not yet studied in the high school. But however, if you look at the example, it is not so difficult to understand. That is some things we call eigenvalues and eigenvectors. In Vietnamese, eigenvalue giá trị riêng, eigenvector vector riêng. Okay, name is name. Just now we need to know what does it mean. So the eigenvalues problem is following. Suppose that we are given an n by n matrix, square matrix like that. You have to know if we can find a non-zero matrix in the columns n by 1 which is so that if we multiply a by x, we get k times of x. That is here. Now if we write it in the formula, that the first one is just only a phrase. Now suppose that a is an n by n which is, and lambda is a number, scalar. And suppose that x is the columns which is not zero. If ax equal lambda times of x, then the number lambda will become the eigenvalue of a. And the vector x, the column which is x here, which has named eigenvector. We call it eigenvector of a. So that is the definition. And the equation like that, because we need to find lambda, we need to find x, so that is the equation. And it has named fundamental equation for the eigenvalue problem. Now you can imagine, once again, one of your exercise will be the following. Given a square which is a, you need to find on the eigenvalue and the eigenvector of that. And here is the examples. First, the previous slide show you the definition, but however, as I told you, whenever you see something very new and something just a little difficult to imagine, please take the simple example. The simple is here. I take very small size, which is of size 2 by 2, A to be that. And suppose that I choose x1 and x2, that is the two columns, which is like that. Now we take A multiplied by x1. Now I suppose that it's very easy for you to do it now. The result is here. You get 5 times of 1, or you get 5 times of x1. So because that, the number 5 is an eigenvalue of A, of some which is A. And the columns x1, the column x1 will be the eigenvector of A. The next one, I multiply A by x2, you get that one. And once again, because that minus 1 will be the eigenvalue of A, and x2 will be the eigenvector. So by that examples, you see, it is, now you can imagine what is the eigenvector and what is the eigenvalue and what is the eigenvector. And however, the second you can know that for one matrix you can have more than one eigenvector, more than one eigenvalue. Here you have 2 eigenvalues and 2 eigenvectors. And your task, your exercise will be, you need to find all possible eigenvalues and all possible eigenvectors. And how we can do that? It is here. Suppose that you are given a matrix A. How you can find all the eigenvalue and the corresponding eigenvector? Here. The first one, because the eigenvalue and eigenvector is given by that one. Ax equal lambda x. That I called you already, that is the fundamental equation for eigenvalue problems. Then from that we get lambda I minus AX. I can explain to you here. The first one, when you have I multiplied by x as a column matrix is equal 1. Ma trận đơn vị nhân với ma trận x thì bằng cái gì ạ? Tính chất đầu tiên học về tính chất của phép nhân ma trận đơn vị nhân với một ma trận A thì bằng cái gì ạ? Ma trận đơn vị nhân với ma trận A thì bằng ma trận A, và nó cũng bằng A nhân với ma trận đơn vị. Okay, so we have the same thing here. Identity multiplied by x equals x. And you can verify that if we take lambda I multiplied by x, you get lambda chi of x. Now on that you have A multiplied by x equals lambda x, and I use that, say it equals lambda I multiplied by x. Now I move that, now I move that pass to here. What do we get? We get lambda I multiplied by x minus A x equals 0, or lambda I minus A x equals 0. So that is, we get that thing. But however, that one is a homogeneous system of linear equation. And in order to find x is a non-zero solution, it means that the homogeneous system of linear equation has more than deviant solution. So eigenvector x must be non-zero. Cái vector riêng đấy phải là khác công, và nó là nghĩa của cái hệ phương trình thuần nhất này. Hệ phương trình thuần nhất có nghiệp khác công khi và chỉ khi định thức của nó bằng không. Lúc này chúng ta có cái tiêu chuẩn là định thức khác không thì hệ phương trình thuần nhất chỉ có nghiệm tầm thường, nhưng ở đây chúng ta yêu cầu là phải có nghiệm không tầm thường, vậy định thức bắt buộc phải không. So lambda, our eigenvalue lambda must satisfy that equation. That equation has named characteristic equation of a matrix A. That is here. So lambda must be the solution for that one. That is, whenever you need to find eigenvalue, you need to write it, you need to solve that equation. The first one, you need to calculate determinant of lambda I minus A, and then you need to solve that system, equation. And here, once again, we go back to our examples. A very small one. We need to find eigenvalue, and it is here. The characteristic equation to be Z1, and that for the square equation like that one, you know it is very easy for you to find. We have a solution lambda equal 5 and lambda equal minus 1. Okay, two things. And for lambda equals, we have two eigenvalue like that. And for the first one, the first eigenvalue lambda 1 equal 5. Now you need to find the system. You need to find this homogeneous system of linear equation like that. It equals 0. Once again, with that you need to find which one is the leading variable and which one is a free variable. And the second is a variable t as x1 equal x2. So now you will have the solution is t time of 1, 1. And I would like to tell you, you need to write the solution must be t is non-zero. Why that? Because eigenvector must be non-zero. If you choose t equals 0, then the solution will become the trivial solution. Nếu ở đây mà các bạn chọn t bằng 0 thì lập tức nghiệm này sẽ trở thành nghiệm tầm thường. And that is not eigenvector. For the second eigenvalue, lambda 2 equal minus 1. Now you see, once again you can solve it, and you will know that. So you can solve it by like that one, and the solution will be t time of 2 minus 1. And again, you need to suppose that t is non-zero because the eigenvector must be non-zero. So that is the first example about how to find the eigenvalue and eigenvector. Now I change it to some a little more difficult, bigger size. Now A is a 3 by 3 matrix like that. Then you are required to find all the eigenvalue and eigenvector of A. The first step, you write the fundamental equation or characteristic equation to be like that one. The determinant of lambda I minus A to be that one. So before that, you remember that calculate determinant is one of fundamental scheme. You need to know how to do it. And then now you get, because that you see, you will have 3 solutions of that. Lambda equal 1, lambda equal minus 1, and lambda equal 3. So you have 3 solutions of characteristic equation. It means that the matrix A has 3 solutions. 3 eigenvalue, lambda 1, lambda 2, and lambda 3, like that one. Now, in order to find eigenvector, you need to write homogeneous system of equation. It is here. Lambda 1 identity minus A to be Z1, and by Gauss-Jordan elimination, you get that things. You see here, at here you see the last variable will be free variable, and then the solution will be the following. Will be here t time of that vector, and once again we need to say that t is non-zero, or otherwise we get the trivial solution. For the second one, lambda 2 now is minus 1. and our matrix will be that one, and the solution will be here. And you please don't forget the assumption that T is non-zero for the eigenvectors. And the last one is here. Lambda 3 equals 3. So that is the third eigenvalue of A. Then you get the coefficient matrix for the homogeneous system to be that one. And again, the solution is here. And again, we meet P is non-zero. So that is okay. That is all principles about eigenvalues and eigenvector. And we will stop about eigenvalue and eigenvector for a while now, and we going back to that notion by the end of the course. I mean, just before the final exams. But however, some of students ask me that why I put the part about the eigenvalue and eigenvector here, because after a while, after two or 3 weeks, you will forget that. Then because here I mean the notion about the determinant of homogeneous system must be non-zero, or must be zero if we want the homogeneous system have a non-trivial solution. Chúng ta cần phải có định thức của hóa chất, định thức của một hệ phương trình tuyến tính thuần nhất, bằng không để cho cái hệ đấy có nghiệm không tuần thường. Nghiệm không tuần thường chính là cái chỗ chúng ta tìm một vector riêng, và vì thế thì cái định thức bằng không sẽ giúp chúng ta tìm được giá trị riêng. Đấy là lý giải tại sao là cái này. Đến cuối giáo trình thì các bạn sẽ học lại cái này rất nhiều, sẽ thường xuyên dùng cái định thức của cái mai trận lambda i trừ dA này bằng không. Nghỉ giải lao thì em. let's continue the class. And once again, please help me to close now. Uh, the last section of the lecture number 3, we tell you about the application of determinant. And we have two different applications. The first one, the determinant will give you another way to find the inverse of a square matrix. You know that to find the inverse of a matrix is not so easy. But here you have another way to find the inverse of a square matrix. And the second one, that is about the Cramer rules. It will give you the formula to find the solution of a system linear equation. And here we begin by that. Suppose that we are given a square matrix A of side n by n. Then we define already the cofactor. And the number of cofactor equals the number of entries inside A. Because A is of side n by n, so we have n square entry. And because that, we have n square cofactor. And if we put the cofactor inside a table like that, we have the so-called the cofactor matrix of cofactor of A. But we are not going to use that matrix. We take the transform of that, we change column into rows, row into columns. We get that one. Here is a record for you. What is the Cij? Cij is minus 1 to the power I plus j of minor. And here I take the transpose of that matrix. We get a new matrix. And that matrix has name adjoint matrix of A. Adjoint matrix of A. I don't know if one of you have the Vietnamese textbook here. Seems that the name in Vietnamese is Ma Chat Phúc Hợp. I don't know. I don't remember. I forgot it. However, it is adjacent, adjoint A. That is adjoint matrix of A. We are going to use that to find the inverse of A. It is here. Suppose that A is invertible matrix, then the inverse of A will be given by that. A is invertible, and then determinant of A is non-zero. Then it is 1 over determinant of A multiplied by the adjoint matrix of A. So in order to find A inverse, you need to find all the cofactors. And you put them together, put them and take the transpose, you get that one. And here is some examples for you. A to be like that. Then we know determinant of A is very easy. AB minus BC. Suppose that number is non-zero. Then we have adjoint of A. Here is very easy. Sorry. No. Adjoint of A to be that number. Then the inverse to be here. A will be that 1 over determinant A multiplied by adjoint of A. And now it is very easy to write down the formula. So you see, for the case of 2 by 2 matrix, it is very easy to find the inverse. And obviously, we always suppose that AD minus BC is non-zero. But now, if you consider that A to be Z1, you have two exercises. The first one, you need to find the adjoint of A, and then the second one, use that adjoint to find A inverse. Then it is here. Recall that Cij to be that number. Then the first one is here. C11 to be that, and that once again, if you remember that last week we calculate on 9 covector here. So I write it here once again. You have everything here. Then the covector matrix of A to be that one. And if we take transpose, you get the adjoint is here. And because that, you see the inverse of matrix A to be that one. And before that, we didn't know what is the determinant of A. But fortunately, the determinant of A equal to 3. It is a non-zero. So we can have A inverse to be that one. And that is the reason. And it requires to multiply one third into that. And you can verify again A multiplied by A inverse equal identity. The second application is the following. Suppose that you are given a system of n linear equation with n unknowns x1 up to xn. Like that. And now we write it in the matrix form. You get Ax equal to B to be Z1. So what is A? A to be the coefficient matrix A to be Z1. And I denoted the column of A by A1, A2, A3 up to AN. So we have n column. And then X and B to be Z1. X is a column of unknown, and B is the columns of right hand side here. Now, what we are going to do is following. And we suppose that the determinant of A is non-zero. If you remember last week, I said something about the Cramer rules. The Cramer rules saying that if A has non-zero determinant, then the system of equation Ax equal to B has unique solution for any right hand side B, and the solution is given by A minus 1 multiplied by B. So we are going to explain it here. We suppose that determinant of A is non-zero. Then suppose that AG will denote the matrix obtained from A by replacing the j's column with the column of B. And here is the picture. Here AG. You see now AG is different from A by the j's column now is replaced by the column B. Then it is here. If we draw it right here. Then we have the following. Then the solution, the system has a unique solution, and solution xj will be given by determinant of a j divided by determinant of a, and that is non-zero already. So that is the solution for. Why you can get that? Because of that things. That, why you can get that one? That is, if we expand the determinant of a j by along the j's columns, you will get that formula. You need to follow the definition from the last week. And here is some explanation for you. Ax equal b, then x equal a inverse multiplied by b. And because a inverse equals 1 over determinant of a multiplied by adjoint matrix of a, to be that. But adjoint of a to be that one, so we write it here. Now if you multiply two matrices here, you will get that the first line will be the determinant of A1, the second will be determinant of A2, up to here, the determinant of A, and because of that, we get what we need. So if J will be to be that one, and the formula inside the bracket on the right hand side is exactly the determinant of A J. So that is what we say about the Cramer's rule. So now you have it. I tell you. So now we have two different ways to solve the system of linear equation. The first one, that is you need to use elimination, phương pháp khử, and the second one is here, Cramer's rule. And you need, in the Cramer's rule, you need to calculate the loss of determinant. So if in your exercise, it requires that please solve the following system of linear equation by using Cramer's rule. But you apply elimination point, then you cannot get the maximum point. Nếu đầu bài yêu cầu các bạn giải bằng phương pháp Cramer thì các bạn bắt buộc phải giải bằng phương pháp đấy, còn nếu các bạn dùng phương pháp khác để tìm ra điểm, các bạn sẽ không được điểm tối đa. Đấy là yêu cầu của bài toán. Nhớ hộ tôi điều đấy. Ngược lại, nếu như yêu cầu dùng phương pháp khử gauss của Jordan mà các bạn áp dụng thế này, các bạn cũng sẽ không được điểm tối đa. Nhớ khi mà làm bài phải nhìn yêu cầu của đầu bài. Okay, the next one will be that will be the examples for you. Here is a system of linear equation, and we know the coefficient matrix is a square, and the determinant is non-zero, is 10, so it is a Cramer's system. And the determinant of A1 to be that, because now you see, you replace the second, the right hand side column into the first column of A to get that one. Next one, determinant of A2 equal minus 15, because now you see the right hand side column of the system now is replaced in the second column of A. And determinant A3 to be that one, and again the third column of A now is replaced by the right hand side column of the system. And then we have our solution will be x to be Z1, Y to be Z1, and Z to be Z1. So that is examples of solving a system of linear equation by using Cramer's rule. So that is the end of the lecture number 3. And because we say that we are just a little late than usual speed, so we need to hurry up just a little while. We continue with the lecture number 4 right now. And the lecture number 4, once again, going back to something which is very familiar to you. So the lecture number 4 deals with the notion of vector space, vector spaces. And now you see, it is very, very long lecture, longer than the lecture number 3. And it is not only seven sections like that. I have one more section as you are going to see now. The first one, I explained to you some things about the vector as we studied already in high school. In high school, we studied already what is a vector. A vector in high school, that is an oriented interval. So oriented intervals. And it is something like that one. You take a straight line, you take an interval of that, you give the beginning point and the end point. It means that you give it an orientation and you get a vector. And usually in high school or in physics, for example, the vector used to represent something like a speed of motions, or you can represent the force or something like that. And for vector, I mean the geometric vector, you can have operation. You can define the operation like addition. In high school, you can got high vector like that. If you are given the vector u like that one, you have the vector v like that one, you put them together. The beginning point of this vector is put at the ending point of the first vector, then you get the sum u plus v to be that is named triangular rule, nguyên lý tam giác. Now we begin the first section here. That is, we are going to define the vector now. The first one, we will define what we call Rn. First, we consider a sequence of n real number, x1, x2, xn. We call it an order n tuple. An order means you cannot exchange x1 and x2. Tôi lấy một bộ n số mà kể cả thứ tự, có nghĩa là các bạn không thể đổi từ x1 sang x2, x2 sang x1. Các bạn bắt buộc phải giữ thứ tự, một bộ có thứ tự như vậy sẽ được gọi là order n tuples. Then the notion n space denoted by a to the power n like that, which has name n space. Chúng ta sẽ gọi là n không gian ký hiệu bởi chữ Rn. That is the set of odd order n tuples. And now, any sequence of n real number like that will be called a vector of I. So now you see, a vector is a sequence of number like that. Please forget the geometric number, geometric vector. Ta sẽ gọi cái dãy như này là vector và chúng ta tạm thời quên cái khái niệm vector là một cái đoạn thẳng có hướng như chúng ta vẫn học ở phổ thông kia. A sequence of n real number x1, xn will be a vector of I. Here are some examples. As I told you, whenever you have something new, you should take the example in very small size. For n equal 1, you have A1. That is one space. One space is the set of all real number. And that in high school you call it đường thẳng thực. It's very easy. Now we continue with n equal 2. It is A2, or we call it 2 space. That is the set of all order pair of real number x1 and x2. And that you know already from high school. In high school you call it the coordinate plane. Mặt phẳng tọa độ. Next, for n equals 3 or 3 space. That is a set of odd order triple of real number x1, x2, x3. That is, in high school you call it không gian. So you, in high school you study hình học không gian. That is something with 3 coordinates like that. But now, that one is not yet in the high school R4. That is 4 space. The set of odd order quadruple or 4 tuple of real number x1, x2, x3, and x4. That is something new for you. The next, we need to define operation on the vectors in n space. Before that, I want to call your attention to the notion in high school. Now, an n tuples like that can be viewed in two different ways in the n space. The first one, it can view as a point, and the second one, it can be viewed as a geometric vector. Here you can see an example like that. A point is here, x1, x2, x3. But it can be considered as a vector going from the origin to that point. And that vector will have two components. The first component is here, and the second component is there. So a sequence of two numbers now can be considered by two different ways. The first one is one point in the left-hand side, picture, and a vector here is a second in the right-hand side picture. Now, suppose that we are given two vectors in n space. U equal U1, U2 up to Un, and V equal V1, V2 up to V. And we consider that U equal V if and only if U1 equal V1, U2 equal V2, up to En equal V. So that is the definition. Then we can define the vector addition, the sum of two vectors u and v. That is a new vector. The new vector denoted by u plus v. It equals u1 plus v1, u2 plus v2, up to un plus vn. So it is very easy. Whenever you find it somehow difficult to imagine, please take n equal 2 or 3. It will going back to what you studied in the high school. The next one will be scalar multiplication or scalar multiple of u by a number c. Here suppose that c is a number, then c multiplied by u will be a new vector. It is a c u1, c u2 up to c un. And so two operations here. Up to now we have only two operations. The first one is addition. The second one we call it scalar multiplication or multiplication with a number. And Zayvin has a name, standard operation in I. Hai phép toán chính quy của không gian RNN. And we can define the negative of u. Negative of u equals minus u1 minus u2 minus u3 up to minus un. Then we can define the difference or the subtraction of u and v. U minus v will be u1 minus v1, u2 minus v2 up to un minus vn. So anything is very simple for you to imagine. And we have the zero vector. Zero vector, that is a sequence of n number, and all the number in the sequence are zero. Zero vector is 0, 0, 0, 0 n times. And now once again I got 0 in Rn is additive identity in Rn, and minus v is additive inverse of v. I will not going into the detailed explanation here. Now I want to tell you some property of that. We have two standard operation of vectors in I in n squared. And now we are going to consider what the properties they have. Suppose that u, v, and w be vectors in I. And suppose that c and d are scalars or a number. Then we have the following property. The first 5 property concerning the addition is here. The first property saying u plus v must be a vector in I. The second property saying that the addition of a vector has a commutativity. The third property saying that the addition has a associativity. The property number 4, property number 5 saying that 0 is identity of addition, and the negative u is the inverse of addition. The next 5 property is here, that concerning the scalar multiplication. And I will not call the name of it here. Those property is very important because we are going to use that. We are going to use that property to define what we call the vector space. And the next week you will see the vector space is now in what we are going to study is no longer geometric object. It will be something like something very abstract. For example, a polynomial can be vectors. You are going to see it. And here is the examples. Suppose that you are given U, V, and W to be that. They are vectors in R4. Then, if you are required to find x equals that, c tie of x equals that, you need to find x satisfying that equation. It is very easy for you. For the first one, you need to do the calculation on the right hand side. Two kind of u minus v plus c tie of w to get that one. But for the exercise number b, it requires you to do just a little more calculation, and finally you get it here. And everything is written in the slide, so you can read it by yourself. And the next will be tell you about the property of additive identity and additive inverse. That is some property about the zero vector and the negative vector. That is, if you have u plus v equal v, then u must be zero vector. That is, the identity is unique. The second property saying that if you have v plus u equal zero vector, then u must be negative of v. So we have two property of zero vector and negative vector. And the property number 3 saying 0 multiplied by, if you take the number 0 multiplied by any vector v, you get 0 vector. And if you take any number c multiplied by 0 vector, once again you get 0 vector. And the last one, the number 5, if you have c multiplied by v equals 0 vector, then you will have c must be 0 number or v must be 0 vector. So that is the property of identity and the negative. Oh, that one is very easy to verify. I will not tell you about that. So the next week we study the linear combination, and linear combination will lead to some very fundamental notion in vector space. That is for next week and for the rest of the course. So before we finish, I have something to tell you in Vietnamese. Ở trên Moodle, các bạn có quiz và trách nhiệm của các bạn là phải làm quiz, phải nộp theo đúng thời hạn ở trên đó. Và hiện giờ là có khá nhiều bạn không nộp cái đó sẽ dùng để chấm điểm vào cuối năm nhé.